It's also week 2, so I know there's a lot going on for each of you guys. Rubber's starting to meet the road. Today is where we said we would jump in on, let me switch mics, where we said we'd jump in on various problems that you can solve based off of the integrals for electric field and Coulomb's law, and so that's really where we're going to want to go today. Maybe you don't want to go there, but that's where we need to go for today. I wanted to remind you guys from last time, this is kind of where we ended up, and I know we kind of flew through it there at the end, but when we're working with differential volumes and differential areas, this is what we're going to be using for the Cartesian system. Again, you got dx, dy, and dz for the volume. One thing that I didn't write up there that I would like to come back to now is that when we're taking a line integral, which is the problem that we're going to start with today, when we're taking a line integral in Cartesian coordinates, what we're going to have is that the differential line element, dl, is going to be equal to dx times I hat plus dy times j hat plus dz times k hat. That is to say that anytime you're doing a line integral in Cartesian space, what this equation says is that the amount the line changes differentially is equal to how much it changes in the x direction plus how much it changes in the y direction plus how much it changes in the z direction. Okay? So that's what we're going to work with first, is we have to consider that dl, a differential line element, is dx times I hat plus dy times j hat plus dz times k hat. And generally what's going to happen is we're going to have, for example, some dot product that we're going to bring this into. And so what you get is that things that change in the x direction, so this I hat here, we only have to consider how dx is varied. Or if it's in the j direction, we only have to consider how y is changing. Or if it's in the k direction, we only have to consider how z is changing. I'll show you how to do that here in just a second. But we're going to be taking these dot products over and over again. So the next one that we talked about was cylindrical coordinates. For cylindrical coordinates, we've got that dv, a differential volume, this little blue, almost rectangular prism, but you can see the front side is slightly larger than the back side, and there's some variation in size along the top and bottom. So what we get is that the differential volume is d rho, which is going to be this direction right here, times rho d phi. If we only multiplied by d phi, we'd only be considering how the angle is changing, not how that arc is changing out along the edge of the cylinder there. So we have to multiply by rho. And d phi is going to be this azimuthal angle right here. And then we've got dz is going to be the vertical side, just like in the Cartesian coordinate system. And you can see that there are 3 differential elements for area that we will end up needing to use potentially. And that is that z hat, that's going to be going out along the top face. The one along rho hat, anything coming out along the outside or going into the cylinder, the rounded edge. Or d phi, anything that's coming in from the side of, say, a cutout of the cylindrical, the cylinder itself. So those are going to be 3 different things. Is this on your equation sheet? No. Do I have to memorize it? No. Again, today is all about deriving results that you're going to use over and over and over again. Today we're going to do it for a line of charge that is uniformly charged, and we're going to do it for a sheet of charge that is uniformly charged. The reason that we're doing this is because after we derive the results that we're looking for today, what is on your equation sheet are the results we derived. That is to say, I don't expect you to do these integrals on your own at this point. We're going to do them together to derive the results so that way you understand when and where to use them when you see them pop up on your equation sheet. For a sphere, we have that the differential volume is going to be dr, moving out along this direction. And then we've got rd theta. Theta is known as the polar angle. It measures from the z-axis to the vector r pointing out from the origin here. And then d theta is going to be how much this angle changes. So we've got dr times rd theta. And then we have to consider the angle phi, the azimuthal angle, how far from the x-axis the projection of r onto this plane is from the x-axis. And we want to consider how d phi changes. And so we end up getting rho, which would be the polar radius, times d phi, or r sine theta d phi. Again, this image is just to help you visualize this. What we need to know today is that dv in spherical coordinates is going to be r squared sine theta dr d theta d phi. And each of the differential areas pointing, going in from the side, that would be the phi hat one. Going out from the radius would be r hat. And then going into the top or bottom of this image here is going to be the theta hat integral here. Fortunately for us, we deal with, in this class, uniform charge densities. And more often than not, we deal with whole spheres. We deal with lines where we'll use the cylindrical elements. And we'll have the Cartesian differential elements, which are easy to solve as well. But what we're after here are pieces to the puzzle that you can use when you get these problems on your homework next week. How do you solve these problems with the results that we derive here in class as example problems? Okay? Any questions? Okay, without further ado then, let's take a look at this first problem that I have set out for you guys. A thin rod of length L and charge Q is uniformly charged so that it has linear charge density lambda is equal to Q over L. Find the electric field at a point P, where P is an arbitrarily positioned point. So I'm looking at this point P here, trying to figure out what in the world is going to be the electric field at that point. And what we want to consider is that we're going to be doing this integral here. Let's call this d sub L. And we're going to be integrating this direction. This is the z-axis, as maybe you can see if you're not at the back. This is the z-axis here. And I'm going to call the point directly underneath my arbitrarily chosen point P. This is going to be z equals 0. Okay. And so what we're after here is we want to find the electric field, E, and we're going to have to integrate over all of the different parts of electric field that come from each of the unique contributions, I should say, that come from the differential element there as I integrate over that rod of charge. Right? You can imagine that from here, there is a d sub E that looks like that. And as I rotate, or as I move this differential element, d sub E eventually is going to point maybe in this direction. So this would be dE from point 2. And then from here, you would have dE, the differential electric field from point 1. And so that's going to sweep between this, then to here, just smoothly through the transition from here to here. And that's what we're integrating over, is all the individual components that make up d sub E. And if we're treating this as an integral over this space, then this would be in the r hat direction. where r is this vector right here. So one way to do this is we could say, okay, there is a z component here, and then there is an r component right here to any of my differential elements. I could break up dE1 or dE2 or my arbitrarily chosen point such that it has a z component and an r component. So what I'm going to do is say, okay, well, dE then can be varied in z. So that would be dE times r hat dotted into z hat. And then I've got that this is equal to, let's see, dE times the cosine of theta. Now, how in the world did I derive that it should be dE times the cosine of theta in this case? Because, maybe what would have been better if I'd shown here, if this is the angle theta right here, then this is the angle theta between, in the r direction, this would be E, this red line is E in the r hat direction. So if I'm taking the dot product between this direction r and little r and this direction z, then we said that A dotted into B last semester is equal to AB, let's write it this way, A dotted into B is equal to AB cosine theta. Cosine theta. Sorry. Well, what is the value, the magnitude of little r hat? 1. It's a unit vector. What's the value, the magnitude of z hat? It's also 1. And so 1 times the cosine of the angle between them is how I end up getting this differential element right here. The other one that we're going to need is dE in the uppercase r direction, which is going to be going along here. And to get that, I get dE times r hat dotted into big R hat. And that's going to be dE times the cosine of, I'm going to call this angle right here, phi. And the sine and cosine of complementary angles are the same, so that would be dE times the sine of theta. If you've ever wondered how you can package up your Algebra 1, Algebra 2, Calculus 1, Calculus 2, and Calculus 3 all into one problem, you've got it right in front of you. And pre-calculus, because we're going to do trig too. So, what I want to find is, okay, what is my total electric field in the z direction, which means I have to integrate over dEz, or that means I have to integrate over dE times the cosine of theta. Well, now we want to know what is dE. What is the differential bit of the electric field contributed by this bit of charge at this point P? Well, this is where we have to bring in what we said before, that E is going to be equal to the electric field from radiating from some point is going to be K times Q over R squared. But that was for a point. What we have right now is dE is K times dQ over R squared. A differential amount of electric field is equal to the constant K times the differential amount of charge that I'm integrating over divided by the distance between the charge and the point squared. And so this is where we have to consider those three different types of differential elements. We said that dq, depending on the geometry, could be lambda dl, or it could be sigma dA, or it could be rho times dV. Here we're dealing with a line of charge, and so what we want to use is this guy right here, the lambda d sub L. So d sub E is going to be equal to K times lambda dl over r squared. And since this is a vector, I have to consider that d sub L is also a vector. So, what direction is my charge changing as I integrate from this left end to the right end? In what direction is the charge changing? It's changing along the z-axis only, right? The reason that that's important is because when I wrote down at the bottom of the page, very early on, dl is equal to dx times I hat plus dy times j hat plus dz times k hat. Well, I'm only integrating over z, and so this is the only thing that I have to consider here is the integral over z. So I've got dE is going to be the integral over k times cosine theta times lambda dz all over r squared. And I'm integrating from, let's call this z1 to z2. And now we have two different choices on our hand as to how to proceed. The first one is you can find what cosine theta is in terms of a distance z. So let this be the distance z right here. And in terms of the distance r, where r is going to be a constant, z is going to be a variable. And then you also have to find r squared in terms of, you'll have to find r squared in terms of little z and big R. And you end up getting a factor of z in the numerator, and you end up getting a factor of z squared plus r squared raised to the power 3/2 in your denominator. You would end up getting something along this line. Z over times dz over z squared plus r squared raised to the 3/2. In which case, if you had followed all of your trig correctly in terms of writing cosine theta in terms of z and big R, then you could look this integral up. I am perfectly fine if you ever find an integral in my class that you feel like you have to work out yourself. Use an integral table or use Wolfram Alpha to solve that integral. But if you didn't have that at your disposal, maybe let's take a look at instead how we could do this with our calculus 2. I want to paste this right here. We aren't going to need that. What we're going to do instead is say, okay, we want to note that in this geometry, the tangent of theta, this angle right here, theta, the tangent of that is going to be equal to r over minus z. And the reason that we do that is because in this case, z is going to be equal to minus r over tan theta. And we've got dz is going to be equal to r, or minus r, times the cosecant squared of theta d theta. So now we have a way to solve this for cosecant squared for dz. What we're also going to end up needing is that the sine of, and I think, let's see here. No, because we're measuring this way, so I need to get rid of these negative signs right here. I do believe. Sine of theta is going to be equal to big R, this opposite side here, over the hypotenuse. So that's going to be little r, or that is that r is going to be equal to r, big R, divided by the sine of theta, or that's r times the cosecant of theta. If you've forgotten at this point, which is fine, 1 divided by the tangent of theta is a cotangent. 1 divided by a sine of an angle is the cosecant of that angle. And then 1 divided by the cosine of an angle is equal to the secant of that angle. Now, the reason that I do this is because I make this substitution and say k is a constant. I'm going to pull that out of my integral. This was an integral from z1 to z2 previously. But now we're integrating from theta 1 to theta 2 of the cosine of theta times lambda. Let's pull that out as well since it's a constant. Times dz. Well, we said dz is big R times the cosecant of theta. Oh, and I forgot a d theta. All divided by, oh, and it was cosecant squared. All divided by little r squared, which we said was r cosecant theta squared. Well, I have cosecant squared in the numerator. I have cosecant squared in the denominator. I have r is going to factor out in the numerator, and that leaves me with a single factor of r in the denominator. And so my big, scary, complicated integral changed to be k lambda over r times the integral from theta 1 to theta 2 of cosine theta d theta. So we have done a lot of trigonometry here to take a big scary integral that would be z over z squared plus r squared raised to the power 3 halves. So raised to the power 3, then square root. And I'm hoping, if you haven't brain dumped everything from Calculus 1, you know what the integral of cosine theta is. What is the integral of cosine theta? Sine theta. Okay, good. Thank you. Made my day. So we've got k lambda over r times the sine of theta evaluated at theta 1 and theta 2. Or that would be k lambda over big R times sine of theta 2 minus sine of theta 1. But most problems are not going to give you what theta 1 and theta 2 are most problems are going to have you solve it in terms of the original variables, that meaning that you know where z1 is from the origin, you know where z2 is from the origin, you know how far away the point is r from the origin. And so what we want to consider is that sine theta 2 right here is going to be the opposite, so big R over the adjacent R2, little r2, and then sine theta 1 is going to be the opposite. I said adjacent, I meant hypotenuse. You've got opposite is going to be big R over hypotenuse R1. And so we're going to rewrite this as that E sub z is equal to k lambda over big R times R over R2 minus R over R1. I can pull out a factor of big R, so it doesn't matter how far away this is, except for R2 and R1 depend on that. So our final result is k lambda times 1 over R2 minus 1 over R1. And it will be up to you guys to figure out what is the value of R2 and R1. Remembering that, for example, R2 would be the square root of Z2, or I got Z2 squared plus big R squared. And R1 would be Z1 squared plus R squared. Maggie?
So on the formula sheet, is it going to give us k lambda and then 1 over R2?
So what is on your equation sheet is, yes, this piece right here, but that would be, we're going to have to derive this R component right here too. I think what's on your equation sheet is going to be what we just derived here. So this part right here times z hat, and then we're going to have to derive the r hat, and I'm going to go a lot faster through that one than I went through this one. I just wanted y'all, again, to know that what pops out on your equation sheet, what is given to you in the text of your book, it's not magic. These things have a reason for where they come from. Now you've seen where it is. And if you take the physics version of EMAG, hopefully you're a little bit better prepared for doing this yourself when you're required to do it yourself. Get an integral table. It's valuable for anybody. I use that more than I pull integrals up on Wolfram Alpha or the internet, because I don't have to type them out, I just have to find them. The CRC handbook, mathematical tables, it's got probably 100 pages of integrals in it. It's ridiculous. It's awesome. CRC handbook for mathematical formulae and tables, or something like that. Any questions on how we derived this part? Okay. We are missing a page here. That's a shame. We are missing a page, so let's slide all of these down. Bummer. Okay, for d sub r, remember that we said d sub r is equal to dE times the sine of theta. And I'm going to go ahead and skip some steps here. We get E sub r is equal to the integral over, in this case, you end up getting your r's and everything cancels, except you get, in this case, k lambda over r times the integral from theta 1 to theta 2 over sine theta d theta. You can go through and convince yourself that's true as a good exercise. But the integral of sine theta is minus cosine or negative cosine theta. So this would be minus k lambda over r times the cosine of theta. And going through and making the same substitution, solving at our boundary points, just like we did before, what you end up getting is, in this case, minus k lambda times the cotangent of theta 2 over r2 minus cotangent of theta 1 over r1. We leave it in the trig form here just because it gets a little bit complicated. But the net result of all of this is E, and I think this might be, or at least the parts of this are on your equation sheet, is k lambda times 1 over r2 minus 1 over r1 in z hat plus k lambda times cotangent theta 1 over r1 minus cotangent theta 2 over r2. Now let's think about this for a second. In this case, let's look at these two versions of my solution here. That I've got E sub r is going to be in terms of cosine theta. I could write it as minus k lambda over r times cosine theta 2 minus cosine of theta 1. Looking at either this solution here, let me star them. Looking at this solution for E sub z, or either of these solutions for E sub r, one of the classic examples that we go to is, okay, what if this arbitrary line of charge becomes infinitely long, right? Another way to visualize it is, let's say you have a 1 meter wire of charge, right? But you're only looking at the electric field, say, a millimeter away from the wire. As far as you're concerned at that point, the wire could appear infinitely long. So what happens to these two solutions if the wire is infinitely long? I know I starred 4 solutions, but 2 and 2 go together. Yeah, right here. Yeah, there'd end up being no horizontal component. So if you look at sine of theta 1, for example, as this thing goes way out here to infinity, then theta 1, no matter how high E sub or big R is going to be, theta 1 is going to drop to 0. And then you get theta 2, if it goes out way this way, it's going to end up being 180 degrees, and the sine of 180 degrees is also 0. And so if my z component, how much it aligns to the horizontal axis here, depends on those two angles, but both of them are sines of angles that drop to 0, then I get that, okay, I get that this portion right here goes to 0. Or you could think of it as, okay, if it's just k lambda, 1 over r2, but r2 goes to infinity, minus 1 over r1, but r1 also goes to infinity. Both of my terms are 1 divided by infinity, which are both 0. And so my horizontal component drops out, and what I'm left with is this problem right here. Find the electric field due to a uniformly charged line that extends to infinity in both directions and has a linear charge density lambda. And we just said that for any line we get E is going to be K lambda times 1 over R2 minus 1 over R1 times Z hat plus cotangent of theta 1 over R1 minus cotangent of theta 2 R2 times big R hat, which I think I might have left that off up here. I did. So what I'm going to do is we've already argued in this case that this term right here drops to 0 because R2 and R1 are both infinitely long. The distance from one end of the wire to where my point is infinitely long, and the distance from the other end of my wire to where I'm measuring is also infinitely long. And it's weird to think about the cotangent of theta over R1, and you've got to think that, okay, that's opposite over adjacent, and R1 is also in there, and we've got all these various terms, but the easier way to write this down is this would be K lambda, and let's choose our second solution with cosine. So this is minus, or let's say plus, actually, plus K lambda over R times the cosine of theta 2 minus the I've got that backwards. Cosine of theta 1 minus cosine of theta 2. Basically, I borrowed from this solution that's now at the top right of the screen. I let the negative sign propagate inside. But we can simplify this further based on this solution. Because again, we said, okay, if, which one's 1 and which one's 2 by how we did this. If my line is something like this is my infinite line of charge here. And this is my point P. Let's actually draw it a little bit closer so it's easier to see here. Well then, in this case, what we get is that as this goes out to infinity, theta, I forgot already, theta 1 is going to go to 0 degrees. And then we get theta 2 is going to go to 180 degrees. So I get plus K lambda over R times cosine of 0 is 1 minus the cosine of 180 degrees is minus 1. And so we get this factor of 2 that pops up in here. We get that this is 2K lambda over R. So if you have an infinite line of charge and you want to know what the electric field at any point is, some distance away R, big R, then this would be what you end up using. This is infinite lines only. Maggie, what was your question?
Big R, what does big R stand for in this?
Good question. Remind me what big R is, and I will do that right now. Infinite line of charge. Big R is going to be this perpendicular distance away from the wire.
So that doesn't change at all despite the fact that it's infinitely large?
Right, because we've chosen some sort of distance R. It could change in the sense that, okay, well, what is it going to be if instead R is up here? If R is this big. So all that's saying is, okay, we still don't get any horizontal component to this, but regardless of if I move this bit here to the left or to the right, I get the same electric field strength at this radius, and I get the same electric field strength for this one as I move this direction. So we only get that as you move further away, your electric field strength is going to drop by a factor of 1 over r. So that's what that equation tells us. Yep. R is the perpendicular distance away from your line of charge, your wire. Any other questions? For the sake of time, I would point you to my solution here on Canvas, but I would, just for the sake of time, let's look here at this problem. Consider a uniformly charged thin disk of radius b and surface charge density sigma. That's the Greek letter sigma there just before the a lowercase sigma, that is. I tend to write it like that. Some people will write it like that. Both look like zeros, if you ask me, but look something along those lines. That's a lowercase sigma. Find the electric field at all points on the axis of the disk. Show that for points on the axis that are far from the disk, the electric field approaches that of a point charge at the origin with the same charge as the disk. Show that for a uniformly charged disk of infinite radius, the electric field is uniform. I'm going to go ahead and spoil it for you. That last result, part C, is going to be the most significant one. We're going to derive later on, when we get to capacitors, how parallel plate capacitors work based on the fact that usually the plates of a parallel plate capacitor are very close to one another and very large, so you can treat them as an infinite disk. So for part A, we want to consider that from this differential area D sub A, if we draw that as a square, that would be a differential area big D sub A. And we want to measure to our point P and call that the vector R, where we're measuring a radius A out to some point B from a radius of 0. And we're going to call this right here our angle theta again. Now this problem has already done a favor for us. They say, hey, look, that differential electric field contribution from that little square that I drew, the differential amount of electric field is straight along the z-axis. But if you look, I actually have to consider that, well, my differential electric field is actually going to be in this direction, down and to the right. So how do they reason that, okay, in essence, the differential electric field from any radius, because that's what they're showing, is for that whole more orange ring there, for any radius should lie on the z-axis. How do they reason that, William? Yes, they end up canceling out. William's right. So what he's trying to say is, if you consider this little square right here, well, on the opposite side of that circle, not quite opposite side of the circle, this opposite side of the circle here, you have another square, and you can consider that each one of them contribute electric field strength that are going to look something like this. And so what ends up happening is the horizontal components always end up canceling out, and what remains is a vertical component. Yes. So in this case, if we look at what we get here, the differential electric field in the z direction, which is all that's going to end up remaining, is going to be equal to dE times r hat dotted into z hat. And just like we had before, we've got the cosine, dE times the cosine of theta is all we're going to end up needing to work with here. I would invite you to follow through on my results, but what we get for the electric field in the z direction here, after we do the integral, because we end up having to integrate over a factor of a in the numerator and the denominator, is z over z magnitude times 2 pi sigma k times 1 minus 1 over square root of 1 plus b squared over z squared. Just for the sake of time, I'm not going to go through all the steps, but when you get to a problem on your homework or on an exam that says, what is the electric field? Some distance z above a circular plate of radius b, this is what you're going to end up using right here. Someone interpretate for me, what is z over z magnitude? What would that give us? Yeah, it's I could write it this way, z over z magnitude. Maybe a better way to write this is E is going to be equal to z hat times 2 pi sigma k over 1 minus 1 over the square root of 1 plus b squared over z squared. Or written as a scalar, which is how it's written up here, that is to say that when you are above the plane, when you are in along plus z, your electric field is in the positive direction. But when you go below the plane, if you were down here, then the electric field is going to point in negative z. So E would look something like this. So all this is doing, another way to write this and how your book writes it, more in engineering notation, is it's called the sine of z, which is z over z magnitude. That is to say, you're just, if z is positive, you multiply by plus 1. If z is negative, you multiply by negative 1. Aggie? Sine of z is going to be, this would be a scalar. This is the scalar form right here. But when I take this into vector form, what I have to do is I end up having to multiply this component by z hat. And z hat, I've already got z hat in, well, I guess that would still have to be sine. It would still have to be, what would be a good way to write that? Maybe a better way to write this would be z vector over z magnitude. Just so that way we're not confused that this is pointing just in the plus z direction. But this is what's on your equation sheet right here. Just because we find, I mean, if we're only talking about a vector in one direction anyway, a positive or negative sign is enough to delineate whether that's going in one direction or the other. So part B asks us something that many of you are likely better scholars than I. Was not a good undergraduate student. And you might be able to find the connection here. I would not have been able to do this. If the point P goes infinitely far away or very far away from the disk is still finite at this point, but if we're infinitely far away from the disk, how do we show that this approximately becomes the electric field of a point charge? What? Yeah, you could do the limit of z approaching infinity. So doing a Taylor or Maclaurin series expansion, actually it'd be a Taylor series expansion about as z goes to infinity. Another way to do it is, since you have a factor of, we're looking as z goes to infinity, z squared raised to the 1/2, you can end up doing the binomial expansion. So the binomial expansion of 1 plus b squared over z squared raised to power minus 1/2 is equal to 1 minus 1/2 b squared over z squared plus, I think it's 1 over 4 factorial, some coefficient, times b to the 4th power over z to the 4th power minus additional terms. But as you go further and further to infinity, these higher order terms are going to drop off very quickly to 0. And so we get e sub z is equal to z over z magnitude times 2 pi sigma k times 1 minus my expansion here. So that's going to be 1 minus 1/2 b squared over z squared, and I drop the higher order terms. 1 minus 1 is 0, so negative that. I get that this is z over z magnitude times 2 pi sigma k times 1/2 b squared over z squared. Okay, I'm still not seeing it. How is that basically that of a point charge? What this is asking is, how is that supposed to be related to Coulomb's law? Help me make some simplifications here. Well, maybe one thing, sigma is equal to the total charge on the disk over the area of the disk. That's how we define the surface charge density. So help me find an area on there to cancel out with the area that's in sigma. Yeah. So I've got let's do this first. I've got 2 cancels with factor 1/2. That leaves me with a factor of pi times b squared. So pi b squared is equal to the area of the disk, and sigma is q over area. So I got z over z magnitude times pi b squared. Well, that's just a times q over a. So those cancel out. All times k. Or that's k. Let me scroll down a wee bit here. K times Q over, or times, let's see here. Oh, I forgot my z squared, 1 over z squared here. Times z squared. And I do have that factor of the sign that could drop in here. But what we were trying to show is this is, in form, Coulomb's law. It's a constant times a charge divided by a distance squared. So yes, when you get infinitely far away from this thing, the thing looks like a point charge. I mean, that makes sense, right? If you were to hold up your iPad or something like that on a football field right in front of you because you're the football coach, that looks like a square rectangular iPad. But as you move up into the stands, that iPad is going to look very, very small. If you move up into International Space Station low Earth orbit, and you were to zoom in on that, it's going to look like an infinitesimally small point. So yeah, it's good that our mathematics fall into what we're looking here, that being that of Coulomb's law.
Would we be able to cross out one of the z's since we have a z squared on the denominator and a z on the
This is still a factor of z over a factor of z. So this is effectively 1. It's plus or minus 1 anyway. So that doesn't give us a term of z that we can cancel. The last part of this, and maybe the most significant result, is show that for a uniformly charged disk of infinite radius, the electric field is uniform. So we're taking this right here. We're taking this right here. Let's copy that. And then put it, say, right here. Is that going to work? No, that's not going to work. Let's put it right here and then move it. We want to take the limit of this. We want to take the limit of this as b goes to infinity, as the radius of our circle goes to infinity. Well, fortunately for us, that's actually quite trivial to do. Why? What's the limit as it goes to infinity?
your b would cancel out, so it just would be the 2 pi times, or whatever that one is, k.
Yeah. So I would essentially get that this term right here, infinity divided by who cares what the magnitude of z is, that's going to be 1 over the square root of infinity. Well, the square root of infinity is still infinitely large, and so we have that this term goes to 0. And so we get that this is z over z magnitude times 2 pi sigma times k. So a problem asks you, you have an infinitely large sheet of charge with some charge density sigma. What's the electric field some height above that sheet? Well, in this case, for the wire, we said that as you get further and further away from the wire, the electric field strength drops off by a factor of 1 over the distance. How does electric field strength change as you move away from the infinite sheet? Does it increase? Does it decrease? It stays the same. This was a question on exam 1 last semester and on my final last semester because people got it wrong after we spent a good deal of time talking about this in class. As you move away from an infinite sheet of charge, no matter how far away from you that you get from it, it still looks like an infinite sheet of charge. Right? And if, no matter what scale you go to, it still looks like you're infinitely far away, that means that since this here is basically plus or minus 1. 2 is a constant, pi is a constant. You've got uniform charge density. That's a constant. K is a constant. Your electric field strength is constant no matter how far away you are from it. So if you could imagine for a second that the earth was indeed flat, and that the flat earth, and I saw some of you, it's not, that the earth is indeed flat and it was infinite in size, then no matter how far away you get from the earth, you would always see that that large infinite sheet of earth is always underneath your feet no matter where you move one direction or the other. There's always vast amount of charge that you can integrate over that's contributing to the electric field that you're experiencing. Now that becomes important because when we get to large capacitors, or capacitors that have their plates so close together, you can assume that the plates are infinitely large. You can bet where we're going to go for the electric field strength, we're going to return to this result right here. I think the way that I asked the question on the exam last semester was, you measure an electric field strength of 1 Newton per Coulomb, a distance of 1 meter away from an infinite sheet of charge. How strong is the electric field strength when you go 2 meters away? And almost every single person put, it's either 1/2 Newton per Coulomb or 1/4 Newton per Coulomb, when the correct answer was that it doesn't change. It's just 1 Newton per Coulomb, right? It doesn't change over an infinite sheet of charge. So, we have discovered how crazily complicated some of these integrals can turn out to be, and how much mathematical finesse you have to solve some of these integrals. And so comes along this guy named Friedrich Gauss, my favorite physicist. We're switching to Minty if you want to join me here. And so we're going to talk about Gauss's law here in just a second. Sorry. But in the meantime, let's take a little bit of a mental break before we knock out the last 17 minutes. Okay, now that we've gotten most everybody, or several of you logged in, let's define first, before we get to Carl Friedrich Gauss, the idea of electric flux. The very technical, scholarly, scientific definition of flux, according to Dr. Waldron, very, very significant here, is that something that goes through something else. I get students that will spend hours upon hours trying to understand the concept that we're about to talk about here and forget this very simple idea that a flux is just something that goes through something else. Take, for example, the HVAC system that is heating this room right now. You get inside the ductwork and you take any arbitrary cross-section of that ductwork. How much air is flowing through that cross-section of ductwork is going to be the flux of air through the duct. That's it. You take a hula hoop, you spray a hose pipe full of water through that hula hoop. Well, the amount of flux of water passing through the hose pipe is going to be the same amount of flux going through the hula hoop. Until you move the hula hoop away, and you still have water coming out of the hose pipe, but now it's not passing through the hula hoop. There's now zero water flux through the hula hoop, but it is still passing through the hose pipe. So we're going to extend that idea to, okay, if we have an electric field, how much electric field passes through some arbitrary area is going to be electric flux. How much electric field passes through some arbitrary area is going to be electric flux. And here's where students get frustrated with this course, Phys 2, because the surfaces that we're going to be working with are going to typically be arbitrarily imagined surfaces. Like I said, some cross-section of a duct. Well, there's not actually something physically there. You just have to imagine that there is some physical area cross-section to that duct. Or that the hula hoop, the contour of the hula hoop, encloses some arbitrary area. Right? But there is no physical area there. The confines of the hula hoop are denoted by the actual outer radius of the hula hoop itself. So mathematically, your book uses a lowercase phi. They're the only book I've ever seen use lowercase phi for flux. Everybody else I've seen, and what I tend to use, is uppercase phi is equal to EA. So electric flux, uppercase phi, is equal to electric field strength times area. Well, this very specific definition only works when the electric field is constant and when the area is perpendicular to the electric field. A problem arises is even if the electric field remains constant, if instead we orient, we're looking at here this plane right here, this light green plane. If we orient the plane with respect to the electric field, well, it doesn't matter that A2 tends to be larger here. What is visible with respect to the electric field is actually the area A1. And so what we're having to do is we're scaling A2 according to what is projected, the area that is seen in projection to the electric field. So we have to multiply using the dot product times the cosine of theta. And so we get that for a constant electric field times some area, that would be A2 in this image, but it's oriented at some angle theta, we have to multiply by the cosine of theta. You ask yourself, does this result make sense? Well, what happens when theta, the distance between the normal, the perpendicular vector from the surface, and the electric field, what happens when theta goes to 0? Cosine of 0 is 1, and when the plane is perpendicular to the field, we get the result that we had on the previous slide. So that checks out. What happens instead if A2, the plane, is parallel to E, meaning that the perpendicular, the normal, is perpendicular to the electric field? Yeah, then we've got the cosine of pi over 2, the cosine of 90 degrees. Cosine of 90 degrees is 0. If the plane is parallel to the electric field never goes through the surface. So you get 0 flux. Both of those boundary results check out. So we're good there. So we've got, for a constant electric field passing through some area where the entirety of the area is oriented at an angle theta with respect to the field, this would be your result. But the unfortunate thing is, I'll come to your question in a second, is the electric field does not have to be constant, and the angle of orientation with respect to the field does not have to be constant. So now we're barking up the tree of integrals again. Right. This is, in my opinion, I wouldn't have drawn these sides here The way I would have drawn this figure is I would have had one plane here, A2, as one plane, and then I would have had plane A1 like this, which was equal to A2 times cosine theta. Don't worry about the bottom part of this angled plane. Don't worry about the front and back side of the plane. The only two planes that matter are the light green plane and then this darkest green plane right here. Normal always means perpendicular. I guess abnormal would be parallel, but no, just kidding. What is the electric flux through the square? Bear in mind that you've got on your devices the extra details. Aha. I think I'm going to surprise most of you. It's equal to 17.3. Thank you for those of you who jumped in afterwards. 17.3 voltmeters, or Newton, whatever the we said. Why is it 17.3 and not 8.66 like the majority of you stated? Anybody? Yeah. Yeah, I gave you the length of a side here, so you have to say 2 times 2 is going to be the area. So that's 4 times 5 is 20. And then you have to take times the cosine of 30, that's 17.3 voltmeters. So a bit of a tricky question, but I've worded it this way because there are other problems in your book on your exam that pop up the same way. And so make sure you're watching for the information that is given. Now, if the electric field is, like I said, oriented or not constant and is not at constant orientation with respect to the surface that you're integrating through, then we have to do this integral here, that phi is going to be integral over the surface S of E dotted into the normal vector times the differential area. If the surface is closed, then this becomes a closed surface integral. They look almost the exact same. They are the exact same except for the integral sign. If you're not familiar with that integral sign because you haven't taken Cal 3 yet, that's okay. All it's saying is the first one is an integral over something like my hula hoop. Or you say the sheet, the front side of my tablet here, right? The front side of my tablet is not a surface that closes in on itself. Whereas instead, if I integrate over the surface of, say, a beach ball, the surface closes over itself. And so integrating over the beach ball, I have to do this one right here, the second one. And that's going to become important when we talk about Gauss's law here in just a second. A closed surface integral is needed when you can define by the surface something that is inside and something that is outside. A closed surface integral is when a surface creates an inside and an outside. If your surface does not create an inside and an outside, then you'd have the surface integral right here. This is important. Electric flux is said to be positive when, say, for a closed surface integral. When something is coming out of the surface, it is positive, whereas if something were going into the surface, it was negative. That, again, will be more evident when we derive Gauss's law here in a second. Because imagine now, we want the electric flux from a positive charge to be positive coming out of this sphere, whereas for a negative charge, we want it to be negative because the electric field are positive and negative likewise for a positive and negative charge, respectively. So we derive Gauss's law. Gauss's law is stated as the net electric field coming out of a closed surface is proportional to the net charge enclosed by the surface. That is to say, net electric field coming out of a closed surface, the electric flux out of an enclosed surface is proportional to how much charge is inside the closed surface. That's it. So right now, it's not telling me what the electric field is at any one of these points on the surface. It's just telling me that the amount of electric field, the net amount of the lines coming out of this enclosed surface, is going to be proportional to the net charge, which in this case is 2q minus q, so that's plus 1q. So the net flux is just going to be based on the net charge. Mathematically, we state that the net flux, or the entirety of this integral here, is equal to q, and the constant of proportionality is known as epsilon naught, the permittivity of free space. Epsilon naught is 8.854 times 10 to the minus 12 farads per meter. We have not gotten to capacitance yet, so we don't know what a farad is, but a farad is amount of capacitance, or a charge per volt. So this could be written as 8.85 times 10 to the minus 12 coulombs per voltmeter. There are two types of problems that you will come to when you do Gauss's law problems. The first one is, what is the electric field at some arbitrary point, just like we solved previously? What is the electric field at some arbitrary point based on a certain amount of charge? Well, in that case, you have to do the integral and compare it to how much charge is enclosed. In this case, this is a bad example because we've got non-symmetry here. But if you're asked for the electric field, you're asked to solve an integral, essentially. The easier problems, and what always trips up students, is what is the net electric flux through a surface based on this amount of charge enclosed in the surface. No integral needed. All you have to do is, it's asking you for phi. You take all of the charge inside the surface, you add it up, and you divide it by epsilon naught. Very easy problems. But being engineers and scientists, we like to overcomplicate it, and you assume you have to do an integral, when all it's asking you is for the flux through a closed surface, which is just proportional to the charge to begin with. It's asking you, do you understand and remember what Gauss's law is? That's it right there. Y'all have a great day. I'll see you on Thursday.